Relativity states that when we observe motion, our observations are always relative to something else. There is no such thing as absolute motion. The motion of an object can only be described relative to something else, other objects, observers, or a set of space-time coordinates. These are called frames of reference. All frames of reference must be in a state of constant motion. They don't necessarily have to be at rest, but they can't be accelerating. This is based on Newton's laws of motion, which always hold true in an inertial frame. Newton's first law states that a body will move with a constant velocity unless an outside force is applied to it. This law treats an object moving with a constant velocity exactly the same as an object at rest. When we extend this to two reference frames moving with respect to each other, we can label either one as being at rest. The laws of physics hold true in all reference frames. This includes the speed of light, which is approximately 3 times 10 to the 8th meters per second in all reference frames. Albert Einstein devised the theory of special relativity. It allows us to better understand the motion we observe at high speeds. Observers in two reference frames moving with respect to each other have different conceptions of space and time because there is no absolute motion. Therefore, when we see an object moving very fast, it appears shorter to us than to someone in the same reference frame as that object. Similarly, the amount of time it takes for the object to travel will seem shorter to someone moving with the object than it will to an outside observer. This effect is called time dilation. In basic terms, time is slower in faster reference frames.
As an example of how to prove time dilation conceptually, let's imagine placing a light clock on a plane. This clock consists of two mirrors facing each other and a photon traveling between the two mirrors. The clock measures time by counting ticks of light, or the amount of times a photon travels up and down between its mirrors. We will simulate this photon with a ball, and the clock will be a person. To the person on the plane tossing the ball, it appears that the ball is moving up and down, but to an outside observer who sees the plane moving relative to his inertial reference frame, the ball follows an arc. If the ball has to travel at a fixed speed in all frames, it is clear that the only way the ball can travel the additional distance as seen by the observer outside is by him perceiving time as moving slower within the moving reference frame. Watch as Brooke simulates this effect. First, she stands still, tossing the ball up and down. We, stationary with respect to her, see the ball move in a straight line up and down. Now, as she moves across the screen, the ball seems to move in an arc, having an additional horizontal velocity.
We saw in our previous example the behavior of a glow-in-the-dark ball being thrown up in the air, as observed from a moving observer, and someone who is observing the person who is not moving, which we can define as an inertial frame. We're now going to use this example to show how someone in an inertial frame observes the events of someone in a moving frame to appear slower, or in a sense, for their time to dilate or take more time. We'll replace the glowing balls from our demonstration with particles of light, or photons, and introduce a very simple device to measure time, a light clock, which is made of two opposing mirrors, in which one tick of the light clock is equivalent to the time it takes for a particle of light to make a trip to the top and to the bottom. For simplicity, however, we'll assume that our observers, Brooke and Noah, are measuring the time it takes for half a tick to take place. Here, our diagrams show that how each person observes the path of light that light travels over time, over the time it takes for 1/2 of a tick. From the diagram, we can construct the size of a right triangle as distances based on the speed of the observer, light, and the time it takes for each event to take place. As shown here, coincides with our right triangle here. What we want to solve here is to show the relationship between Brooke and Noah's clocks measured from a half a tick. We can solve for delta t by plugging these distances into the Pythagorean theorem, and with the corresponding legs and hypotenuse of the triangle corresponding to the Pythagorean theorem, which is c squared equals a squared plus b squared. After a lot of algebra, shown here, we see that relationship is delta t, which is the time that Noah observed, equals the delta t prime, which is the time that Brooke measures from her light clock, over the square root or 1 minus b squared over c squared.
Time dilation allows us to travel vastly greater cosmic distances in a human lifetime. Let's figure out how far we could travel in the universe in a lifetime without time dilation. Well, it takes light 80 years to travel 80 light years, so for us to travel 80 light years it must take more than that, because we can't travel at or faster than the speed of light. For example, at 99% the speed of light, it would take just under 81 years to travel that distance without time dilation. So we couldn't travel more than 80 light years or so in a lifetime without time dilation. With time dilation, though, these trips take significantly less time. To redo the same scenario with time dilation, it would actually take 11.5 years according to the people on the ship. Traveling very great distances in the universe is also possible thanks to time dilation. The center of the galaxy, for example, is 25,000 light years away, but with time dilation, a ship going at 99.9999% the speed of light, just under the speed of light, could leave Earth and reach the center of the galaxy in 35 years according to the people on the ship.
That's not good enough for us. But this we could use. Highly radioactive spent uranium fuel from nuclear power plants must be isolated into solid bedrock with stable and predictable conditions far into the future. Finnish bedrock is 2 to 3 billion years old. This rock will be here for a very long time. We can still see traces left by people from thousands of years ago. Some things endure and last for a long time. The Great Pyramid of Giza in Egypt is 4,500 years old. On the Earth's surface, man-made structures are constantly susceptible to the effects of the environment. Below ground, however, the process of change is much slower. Tutankhamun was discovered in 1922, along with many ancient treasures, including a well-preserved golden mask. Isolated from the environment, this metal artifact had remained in perfect condition for 3,300 years. The metallic fuel elements containing uranium are packed inside a copper canister, which is then disposed of deep into the bedrock. Under proper conditions, copper resists corrosion for a very long time and retains its protective properties. Deep in the bedrock, the canister is surrounded by bentonite clay in a deposition hole. Bentonite clay is a natural material that, when wet, expands to seal all openings. The clay isolates the canister completely from its surroundings, preventing any movement of water near the canister. Many examples from nature and human history prove that it is possible to isolate spent nuclear fuel from the people and nature. Once the spent fuel is isolated into the bedrock, it poses no danger.